So in this video, I'm going to go through the start of chapter 9, so the Pythagorean Theorem. So we have our right triangle, and we're just going to name some vocabulary. So this is called the hypotenuse, the side that's across from the 90-degree angle. And so we're specifically going to be working with right triangles. And the other two sides, sometimes we call them legs. Eventually we'll call them something else as well, but for now the hypotenuse is the important one to always identify that. So then to find the Pythagorean theorem, maybe some of you already know what it is, but if we say each square is 1 centimeter by 1 centimeter, then B would have a length of 3 and A would have a length of 4. And then to find C, since it's like diagonal, I've moved this square over here, and then we can see that it has a length of 5. And so then it says find the area of the square on the hypotenuse. So the area of this square would be 5 times 5, which is 25. Okay, and then it says draw in the squares of length A and B. So drawing this square, 1, 2, 3, 4 by 4. These should be straight lines. So this square would have an area of 4 squared, which is 16. So I'll circle these. And then if we draw in this square, a 3 by 3 would have an area of 9. And so then what the Pythagoreans noticed was that if you took the A value and squared it and then added it to the B value, you would get the C value. So 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. And they found this is only true for right triangles and no other kind of triangles. And it doesn't matter which value is A and B, but C has to be across from the right angle. Because notice if I just switch the order, 16 plus 9, it's still equal to 25. So this is our equation or formula for the Pythagorean theorem. It's very famous. Most people, this is the only thing they actually remember from geometry if you ask them years later. So maybe ask your parents if they remember that. So a little bit of history about Pythagoras. He lived to be 75 years old. He was a Greek philosopher, mathematician. He's been given credit for this, but actually there's a lot of proof that would show, or evidence that would show the Babylonians and Indians were using it. But it was never proven until the time of Pythagoras. As in, they proved that this works for every right triangle, no matter what, even if the sides aren't whole numbers. So some examples, just identifying. So it says find C, so we would plug in 12 squared plus 15 squared equals C squared. Okay, and then we just multiply, add these up, and we get 369. And then to find C at the end, we take the square root. Okay, and the square root of 369 is about 19.2, and it keeps going. So this is gonna give us another chance to practice with rounding. So let's just say to 1 decimal place, in this case, 19.2. And then for the second one, we know the hypotenuse. So that's our C value. And so A squared 5 would be the B value. Oops, let's plug in 5 there. And so if I do 5 times 5 is 25, and 13 times 13, now I have to subtract this value over here. So when you're solving for A, it's a little bit different than when you're solving for C. So then this becomes 144, and then I take the square root, and I get 12. So then the last one, again, I'll always identify the hypotenuse first because that goes on on its own side of the equation. So then 6 would be A and B is what we're trying to find. So then you could rewrite this. Actually, you can subtract 6 squared. Some people just go right to this and they say, well, if I know the hypotenuse, I'm going to do that value minus the other value. So that makes it a little bit easier. So b squared would equal 64 minus 36. 64 minus 36 is 28. And then if that number is not a perfect square, we're going to have to round. So the square root of 28 is about 5.29. So we'll round that to about 5.3. Okay, and then the converse of the Pythagorean theorem just says if the reverse. So I'll ask you questions like this: Will these side lengths make a right triangle? And all you have to do is pretend like the biggest one would be the hypotenuse, and then see if the other two add up. So in this case, we'd have to do 13 squared plus 18 squared, and ask, does that equal 22 squared? And for this one, 8 squared plus 15 squared does equal 17 squared, because 64 plus 225, 17 squared is 289. You can check that. It works. But for this one, it fails. So we would say this is not true. You can check this. 13 squared is 169. 18 squared is 324. And that does not add up to 484. So we would say this does not make a right triangle, and this one does. So I'll ask you different kinds of questions like that. And then, if three positive integers that work in the Pythagorean equation, we would call those Pythagorean triples. So like the 8, 15, 17, some other really famous ones, 3, 4, 5, 5, 12, 13. So if you recognize these, you can sort of memorize them, and you won't have to even use the Pythagorean theorem. So there are infinitely many of them. And now this is just a problem we can solve using the Pythagorean theorem. To find the area of the triangle, we need base times height divided by 2. But we don't know the height in this case. And so since this is already split into a right triangle, we would know this side's 5. So we can do 5 squared plus the height squared, set that equal to 12 squared, since that's the hypotenuse. And then we can plug it through and subtract 25 and figure out what the height is, which is the square root of 119. So that's about 10.9. And now it's important not to round this too far, because we're going to use it and now do base times height. So multiply that times 10 and then divide the whole thing by 2. And when you do that, you get about 54.54.